Hello, welcome to chapter 9.1. Today we're going to learn about sampling distributions. We have to do a little review first. Uh, we have to talk about a parameter and a statistic. A parameter is a number that describes a population. In statistical practice, the value of a parameter is not known because we cannot examine an entire population. That's like if I want to find the mean of males. I can't take all of the males in the entire world and find their mean height. But I can find a sample, and find their mean, and that would be a statistic. A statistic is a number that can be computed from sample data without making any use of unknown parameters. In practice, we often use a statistic to estimate an unknown parameter. So we can find 200 randomly chosen males, find their height, and take the mean of that. And that is a good prediction of the parameter, which is the height of the mean height of men, what we would be looking for. Now we use different symbols for the population mean and the sample mean, and this does get a little confusing because if we're talking about a population mean, then we use a mu. When it's a sample mean, it's an X bar. And we've been doing this all year, we just haven't told you explicitly that this is what we're doing. We also have a population proportion. So if I found 45% of the people in my sample, or that would be p hat if it's a sample. And if it's the population proportion, it would be just p. Same situation. The population proportion would be, say, all Americans, and the sample proportion would be just the people that we randomly chose out of our population of Americans. So if this is our entire population, we're just going to ask a small section, and that's going to be our sample. A poll asked 515 people whether they believed in ghosts, and 160 said yes. So 0.31 is this the population proportion or a sample proportion? Hopefully everybody is saying it's the sample proportion. So we can write this p hat is equal to 0.31. And this is pronounced p hat. It's got a little hat on it. Alright, if we polled 515 more people, would exactly 160 say yes next time? That answer is probably not. It's possible, but I would guess that not 160 people would say yes the next time. So there's some variability, and we call that sampling variability. Each sample could be different from the previous sample, and how much variability tells us a lot about the true proportion. A customs office uses a machine that lets 70% of the people through, and 30% of the people get searched. If we pick 50 people to go through the line, we can use random number charts or a calculator to figure out how many people actually go through. So what we'd do is we'd want to do random integer. We're going to have we're going to pick numbers, say 1 through 10, and we're going to pick 50 of them. Now, this is just going to be a simulation, and we're going to say numbers 1 through 3 mean that they get searched, and 4 through 10 mean they go through. Now, I'm doing this at home, and I don't have a fancy calculator to do this along with, but you can do this and count up how many people get searched, and you'll have some number over 50, and that number should be pretty close to 0.3, but it probably won't be exactly 0.3. So you can figure that out, put that number over 50, and you'll get your p hat. If we did this many times, we would get a histogram that would look like this. This is, I guess, for the people who go through, right? Yeah. So 70% of the people go through, and most of the time you get 70%, or around 70%. But sometimes you'll get a little bit more, sometimes a little less, and it's going to be rare when it gets out to 82% or 58%. So the sampling variability in this particular study will be between about 58% and 82%. The sampling distribution, this is called the sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic and all possible samples of the sample size from the sample population. So this right here is a sampling distribution. Many samples are compiled to see what the actual population is. Now, in class, we're going to do something, and you can do this at home. What is the distribution of random digits between 0 and 9? So we don't need a 10 here. Let's do this with 50 numbers. So if I just did random integer, we're going to go from 0 to 9, and we're going to pick 50 of them. And then put that into list 1. And if I wanted to graph that, I would just go to stat plot, turn on your stat plot, and you can do a histogram. And what you'd see is something that's relatively straight across. Because this would be considered a uniform distribution. Now, since there's distribution, I should finish writing before I start talking. All right. Now, you might have one thing up and one thing down, but in general, if we did this many times, it would average out to be a straight line. So if I'm describing the sampling distribution, I would say its shape is a uniform distribution, its center is around 4 or 5, its spread is between it has a range between 0 and 9, and it does not have any outliers. All right. Now, if I did something else and I picked 2 random digits and I found the mean of them, so if we have this in L1, let's do the same thing and send another one to L2, and then L3 can be L1 plus L2 divided by 2. So I'm finding the averages. So do that. Pause the video, take some time, graph it. All right. Hopefully you're done. And so that was if you did it 50 times. If you did it 200 times, it would look like this. It's not a normal distribution. It's kind of it's not really bell-shaped as much as kind of a triangular shape. But if we're finding the average, there's going to be a lot more ways that we can get 4.5 as an average than we can get 9 for an average. So 4.5 would come up more often than 9. The only way we can get a 9 for an average is if we get a 9 on the first digit and a 9 on the second digit. And that's going to happen pretty rarely. Same with 0. To get 0 and 0, that's the only way we can get 0. And it's pretty rare when both our first digit and our second digit are going to be 0. So you can see the distribution is something like this. And in this table up here, I have how many different ways we can get 0.5. We could get a 0 and a 1, or a 1 and a 0. So there's 2 ways to get 0.5. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways we can get 4.5. So when we find the average, we get a much different graph than our uniform distribution. All right, now we're kind of on to a new topic, or not completely new, but we're going to talk about a bias of a statistic versus the bias of a sampling method. We can have a sampling method. We learned about bias and sampling methods where it systematically favors certain outcomes. A bias in a statistic means that the statistic is not going to be accurate for the population that we want to get. So we want to look for an unbiased statistic or an unbiased estimator, which is a statistic used to estimate the parameter. Well, it's unbiased if the mean of the sampling distribution is equal to the true value of the parameter being estimated. The statistic is called an unbiased estimator of a parameter. So we want the mean, if we're finding means, and we're doing a sampling distribution of a mean, the mean of those should be equal to the parameter that's being estimated. The variability of the statistic is described by the spread of the sampling distribution. The spread is determined by the sampling design and the size of the samples. Larger samples give smaller spread. As long as the population is larger than the sample, say at least 10 times larger, the spread of the sampling distribution is approximately the same for any population size. So, thinking about a target, this would have high bias but low variability. All of the data points are close together, but they're not a very good estimator of the true proportion. This would be an instance where we'd have low bias but high variability. It's not very good at estimating it, but at least it's getting in the right direction. You're missing the same distance all around. If this is a case where you have a high bias and high variability, you don't hit the target, and it's a pretty loose connection. Your ideal situation is if you have low bias and low variability, so you can, you know that it's very close to what you're estimating, and there's not a lot of variability. Properly chosen statistics computed from random samples of sufficient size will have a low bias and low variability. If you increase the number of samples, the variability will decrease. All right, and that's enough for today. Good luck with this one.